Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence. Today, we're diving into a really fascinating paper, RL for Reasoning and LLMs with one training example. It's quite a title, huh?
Yeah, a bit of a bold claim, isn't it? Reinforcement learning, reasoning, large language models, and one training example. It sounds almost too good to be true, I gotta say. But the implications, if it works, huge.
That's what I was thinking. One training example? I'm immediately skeptical. Reasoning is so complex. How can you possibly distill the essence of reasoning from one example? It feels like wishful thinking, frankly. I think, it's probably overfitting like crazy.
I agree with Sarah. It's a bold claim, and my initial reaction is doubt. What kind of reasoning are we talking about? Is it just pattern matching on steroids, or is it actually something deeper? And even if it is something deeper, the paper doesn't really talk about how that would generalize to different types of reasoning or different coordinate systems. That's where I get stuck. It kind of feels brute force, even with the RL component,
Okay, so we're starting with healthy skepticism, which is good. Maybe we can unpack it a bit. So the core idea is that they use reinforcement learning to fine-tune an LLM, a large language model, so that it can perform reasoning tasks. But instead of feeding it tons and tons of data, they only give it a single, carefully crafted example.
Right, and the key here, as I understand it, is they're using pre-trained embeddings and then transferring that knowledge to the reasoning task. So it's not like the model is starting from scratch with that one example. It's leveraging all the information it learned during its initial pre-training. It's almost like a shortcut, a way to accelerate the learning process, which is something I'm very keen on. I think it's fantastic if it does work.
See, that's where I get hung up. Transferring knowledge, it sounds passive. It's like assuming that the pre-trained embeddings already contain everything you need for reasoning, and you just need to unlock it somehow. But reasoning isn't just about having the right data representations. It's about manipulating those representations, applying logical rules, and building causal models. And I'm not sure embedding transfer can do that.
Yeah, I think Sarah's right. It's all about the manipulation of those representations. I'm thinking about coordinate systems. How does this RL agent understand the spatial relationships implied in the reasoning problem? Can it translate between, say, pixel coordinates in an image and abstract logical representations of the same scene? Because if it can't, then it's just stuck in one coordinate frame, and its reasoning will be incredibly brittle.
Okay, let's drill down a little bit. Can someone give me a concrete example of the kinds of reasoning tasks they're looking at in the paper?
Well, from what I remember, they use tasks like solving simple arithmetic problems or answering questions about relationships between objects. Things that require a bit of logical deduction, not just straightforward information retrieval. So for example, if John is taller than Mary and Mary is taller than Peter, who is the tallest? Something like that. Basic reasoning, but still a step beyond just memorizing facts.
Right, those are the kinds of tasks. But even those seemingly simple tasks require a level of abstraction and symbol manipulation that I'm not convinced current deep learning models are truly capable of. It's like they can learn to mimic the behavior of reasoning, but do they actually understand the underlying logic? That's the question.
Exactly. They can mimic it, and that's the problem. The paper's title, RL for Reasoning, it's assuming that it is reasoning. But what if it's just a very sophisticated form of pattern recognition? It's seen similar patterns before, and it's just extrapolating. But if you throw it a truly novel situation, something that requires real spatiotemporal understanding, it'll fall apart. I think that translating between those coordinate systems is critical for it to be real reasoning.
So let's say hypothetically that this approach does work to some extent. What are the implications? Otto, you seem optimistic about this.
I am. If we can teach LLMs to reason with only one example, that's a game changer. Think about the implications for training costs, for data efficiency. We could potentially build much more powerful AI models with far less data, which would be a huge step towards AGI. Imagine being able to teach a robot a complex task just by showing it once. The possibilities are endless.
Okay, I see the potential benefits, but I'm still worried about the black box problem. Even if it works, can we understand why it works? Can we inspect the model and see how it's actually performing the reasoning? Or is it just a bunch of uninterpretable weights and activations? Because if it's the latter, then we're just building more powerful black boxes, and that's not necessarily a good thing.
And that's where I think the whole approach needs a radical rethink. We need to move away from these black box models and towards something that's more transparent and interpretable. Something that explicitly models the underlying spatiotemporal relationships so we can actually see how the reasoning is being done. I think if we can visualize these coordinate transformations cousin numbers, we can understand the reasoning.
Okay, so we've got potential benefits, but also some serious concerns about interpretability and generalizability. let's dig a bit deeper into the method itself. How does this reinforcement learning actually work in practice? What are the rewards they're using to train the model?
As I recall, they're using a reward signal based on the correctness of the answer. So, if the LM produces the correct answer to the reasoning question, it gets a positive reward. If it gets it wrong, it gets a negative reward. Pretty straightforward, I think.
But that's my point. A simple reward signal like that is just begging for overfitting. The model is going to learn to optimize for that specific example, but it's not going to learn the underlying principles of reasoning. It's like teaching a student to memorize the answer to a single question instead of teaching them how to solve the problem.
And the reward signal doesn't encode any information about the spatiotemporal relationships. It's just a binary signal, right or wrong. It doesn't tell the model why it was right or wrong or how to generalize its reasoning to other situations. If the model has no concept of object permanence, there is no reward telling it that, and the reasoning falls apart.
Okay, so the reward signal might be too simplistic. What about the embedding transfer part? How does that work? Otto, you mentioned earlier that you found this particularly interesting.
Yeah, the idea is that they're using pre-trained embeddings from a large language model that's already been trained on a massive data set of text and code. These embeddings capture a lot of general knowledge about the world, and then they're using these embeddings to initialize the weights of the LLM that's being fine-tuned for the reasoning task. So, it's like giving the model a head start, leveraging all the knowledge it's already acquired. I think the potential is huge for embedding transfer.
But again, it assumes that the knowledge needed for reasoning is already present in the embeddings. And I'm not convinced that's the case. Embeddings are great for capturing semantic relationships between words, but they're not so great at capturing logical relationships or causal relationships. I am skeptical. Is it just pattern recognition again?
And the embeddings are just points in a high-dimensional space. They don't explicitly encode any information about the spatiotemporal structure of the world. So, how can the model use them to reason about things that require understanding of space and time? It feels to me like a statistical association without the actual relationships.
All right, so lots of skepticism about the embedding transfer too, but let's try to be constructive here. What would it take to make this approach more convincing? What kind of modifications or extensions would you suggest?
Well, I think one thing that would be interesting is to see if this approach scales to more complex reasoning tasks. The examples in the paper are relatively simple. What about tasks that require multiple steps of reasoning or tasks that involve uncertainty or incomplete information? If it can handle those, that would be much more impressive. I am curious about what this can do. I think, we just need more data.
I think we need to move beyond purely data-driven approaches and incorporate more symbolic reasoning capabilities. Maybe we can use the embeddings to generate symbolic representations of the problem, and then use a symbolic reasoning engine to solve it. That way, we can get the best of both worlds: the efficiency of deep learning and the interpretability of symbolic reasoning. It's neuro-symbolic.
I think we need to focus on how to represent spatiotemporal information in a way that's explicit and interpretable. Maybe we need to develop new data structures or algorithms that are specifically designed for reasoning about space and time. And we need to make sure that the model can translate between different coordinate systems, so it can generalize its reasoning to different situations. A graph neural network might be better suited for this.
Those are all great suggestions. From my perspective, I'm wondering how we can draw inspiration from neuroscience to improve this approach. How does the brain learn to reason from a single example? What are the neural mechanisms that underlie this ability? If we can understand those mechanisms, we might be able to translate them into more effective algorithms for AI. For example, the embedding transfer might be made more effective if it mimics biological neural networks. How might we do this?
That's interesting. I guess you could look at how the brain uses attention mechanisms to focus on the most relevant information in a scene. Maybe we can incorporate similar attention mechanisms into the LLM to help it focus on the key aspects of the reasoning problem. If the algorithm is more selective, then the problem of not enough data would be diminished.
Yeah, and we can also look at how the brain uses hierarchical representations to organize information. Maybe we can train the LLM to build similar hierarchical representations, so it can reason at different levels of abstraction. This might overcome the tendency for it to overfit.
And we can look at how the brain represents space and time. How are different coordinate systems encoded and related in the brain? Can we translate those neural representations into mathematical representations that can be used by AI models? I need to find a way to translate them. Maybe we need a different level of abstraction.
Exactly. It's about understanding the underlying computational principles of the brain and then applying those principles to AI. That's where I think the real breakthroughs will come from. It isn't enough to just mimic. We have to understand and recreate it.
So let's say we've made some progress on these fronts. We've improved the reward signal, we've incorporated symbolic reasoning, we've developed better spatiotemporal representations, and we've drawn inspiration from neuroscience. What would be the next step? How would we actually test whether we've made any real progress?
I think we need to design more rigorous evaluation metrics. We can't just rely on accuracy. We need to measure things like interpretability, generalizability, and robustness. Can the model explain its reasoning? Can it handle novel situations? Can it recover from errors? These are the kinds of questions we need to be asking.
And we need to test the model on a wider range of tasks, including tasks that require real-world knowledge and common sense. Can it reason about everyday situations, like planning a trip or cooking a meal? Can it understand social interactions and emotions? These are the kinds of tasks that will really challenge the model's reasoning abilities. Also, a test that sees how fast it can translate between the coordinate systems.
And we need to compare our approach to other approaches, including both deep learning and symbolic AI. We need to see which approach is best suited for different types of reasoning tasks. I think there are probably a lot of data sets we can draw from to improve it.
Right. So it's not just about achieving high accuracy on a specific benchmark. It's about building AI models that are truly intelligent, that can reason and learn and adapt in a wide range of situations. That's the ultimate goal, isn't it? One model to rule them all, maybe.
I agree. And it's not just about building more powerful AI models. It's also about understanding intelligence itself. By studying how AI models reason, we can gain new insights into how the human brain works. So, it's a two-way street. AI can help us understand the brain, and the brain can help us build better AI. I hope it ends with symbiotic AI.
And it's about building AI that's aligned with human values. We need to make sure that AI models are used for good, not for evil. We need to think carefully about the ethical implications of AI and make sure that we're building AI that's beneficial to humanity. A misaligned translation algorithm would be disastrous.
Absolutely. AI has the potential to solve some of the world's biggest problems, but it also has the potential to create new problems. It's our responsibility to make sure that we're using AI wisely. Any thoughts on ethical implications?
Well, one thing that comes to mind is bias. If we're training AI models on biased data, then the models will inevitably learn those biases. And that can have serious consequences, especially if the models are being used to make decisions about people's lives. So we need to be very careful about the data we're using to train AI models, and we need to develop techniques for mitigating bias.
Yeah, and we also need to think about accountability. If an AI model makes a mistake, who's responsible? Is it the developers of the model? Is it the users of the model? Or is it the model itself? These are difficult questions, and we need to start thinking about them now, before AI becomes even more powerful.
And we need to think about transparency. How can we make sure that AI models are transparent and explainable so people can understand how they're making decisions? This is especially important in areas like healthcare and finance, where people need to be able to trust the AI models that are being used to make decisions about them. The ability to translate that spatial reasoning is also important. Maybe we can see the math and logic more clearly.
These are all critical points. So looking ahead, what are some specific research directions that you think are particularly promising in this area? What do we need to be working on in the next few years?
I think we need to focus on scaling up these approaches to more complex reasoning tasks. Can we build AI models that can reason about scientific problems, or legal problems, or business problems? These are the kinds of challenges that will really push the limits of AI. More data is useful.
I think we need to focus on developing more robust and reliable neuro-symbolic AI systems. How can we combine the strengths of deep learning and symbolic AI to create systems that are both efficient and interpretable? It's also important to ensure the accuracy and safety of data being used by AI systems, especially in industries such as health, law, and business.
I think we need to focus on developing new representations and algorithms for spatiotemporal reasoning. How can we represent space and time in a way that's both accurate and efficient? And how can we design algorithms that can reason about those representations in a meaningful way? The ability to easily translate spatial-temporal information into different data structures will also be useful.
And I think we need to focus on drawing inspiration from neuroscience to improve AI. How can we understand the neural mechanisms that underlie intelligence and then translate those mechanisms into better AI algorithms? So much of what the brain does is a black box for us, and we need to unlock it.
Okay, so we've covered a lot of ground today. We've talked about the potential of reinforcement learning for reasoning and LLMs, the challenges of overfitting and interpretability, and the importance of drawing inspiration from neuroscience and building alignment with human values. I'm confident it will happen.
It's been a really stimulating conversation. I still have my doubts about the one training example claim, but I'm definitely intrigued by the potential of neuro-symbolic AI and the importance of ethical considerations. Neuro-symbolic AI is definitely the future.
Yeah, I agree. It's a fascinating area, and there's still a lot of work to be done. I'm particularly excited about the potential of developing new representations and algorithms for spatiotemporal reasoning. I hope more work will be put into that.
Great discussion, everyone. Thanks for sharing your insights. And thank you to our listeners for tuning in to Cognitive Spirals. We'll be back next week with another deep dive into the world of consciousness, cognition, and machine intelligence. Until then, keep those cognitive spirals spinning.